vector sign here means that we could break these down into components, px, py, pz, and they're proportional to vx, vy, and vz. Linear momentum looks like this. What would the angular version look like? You go, okay, here's my first guess. My first guess would be angular momentum, again, I'm going to take out the m and put in what? Rotational inertia. I'm going to take out the v and put in what? Omega. And then I'm going to take out the p and I'm going to put in angular momentum. Now, you figure p, how much sense did that make for linear momentum? Why would we use a symbol like p? I don't know, it's just kind of out of the blue. So we're going to do the same thing with angular momentum. We're just going to pick out L, right? That seems just as sensible as using p for linear momentum. Now, our first guess for this is L is equal to I times omega. Are these vectors? Yes, these are also vectors. So what we're going to do is we're going to say angular momentum is equal to I times rotational velocity. But there's a problem with this. Let's see. If I take this object and I hold it like this and I measure its mass, and then I hold it like this and I measure its mass, how does that compare?
Oh, the mass distribution.
It's the same, right? The masses are the same. So in this formula, m's just a scalar. Doesn't matter what direction the object's moving in, m's always going to be the same. If I take this object and I rotate it around this axis, and then I rotate it around this axis, are the rotational inertias the same?
No.
No, they're different, right? So rotational inertias are not as simple as mass. Mass is just a straight scalar. And that says that we can take the momentum and say it's directly proportional to velocity and keep using the same m value no matter what direction we're moving. But when we start rotating an object around different axes, the rotational inertias will be different. Now, it's not a complication that we're going to go into in great detail, but I want you guys to be aware that this is actually something that's more complicated. Jake, how many of you guys have done matrix multiplication? So we have to set this up as a 3 by 3 matrix. So this actually is a matrix. We're not going to do any calculations like this. The book kind of hints at this. And it says to get the 3 components of angular momentum, we actually have to multiply by a matrix of up to 9 elements. There could be 9 elements in that matrix. And relate that to the rotational inertia. So it is more complicated. Again, we're not going to go there. We're going to stick with the simplest sort of problems. So the simplest sort of problems have, if there's enough symmetry, then it's simple. If there's enough symmetry, then we can identify the rotational inertia and just say that they're directly proportional. Okay, and again, the textbook shows some examples of where it's not going to be symmetric, but they just show that it's more complicated than what we're writing now. So I guess the take-home lesson from this is, when we do these comparisons between linear and rotational motions, so many things line up, right? We went all the way down this column in the linear stuff, we went all the way down the column in the rotational stuff, the concepts, and we made a connection between them, but there are some things that are a little different between linear and rotational motion. All right. So in fact, I'm going to go ahead and erase this as if it was never here. Okay, so what that says is, if I've got an object, and again, we'll get something that's fairly symmetric. Let's say I have a sphere or something. So here's a sphere. Maybe this is the Earth. Let's say here is the Earth, and the Earth has rotation to it. How much angular momentum is there in the rotation of the Earth? How would we calculate that?
We can find it.
Yeah, this seems to be saying that what I would want to do is say that the angular momentum is equal to rotational inertia times omega. We're going to measure the rotational inertia here.
From the center.
Yeah, it's around the axis of rotation. So wherever the axis of rotation is, so we'll say this is our rotational axis. And I've got some motion around that. Here is my omega. What should I use to calculate the rotational inertia of the Earth? 2/5 mR. Yeah, that seems reasonable, right? So I'm going to say the rotational inertia here is 2/5 m, where m is the entire mass of the Earth, r squared, where r is what?
The radius?
Yeah, it's the radius. So we'll say this is the radius of the Earth. Okay. Is that a really good way to calculate? It's going to be accurate to within 1 or 2%, or is it going to be off? And if it's going to be off, why? Yeah.
The mass is distributed uniformly.
Exactly. So this formula was derived with the assumption that everything was uniform density. Is the Earth uniform density?
No.
Not really.
No, the denser stuff has dropped farther towards the core. So as you drop down into, and then there's higher pressure there. So as you drop into the Earth, you're getting denser and denser regions, denser materials under higher pressure. So this is kind of an approximation. We're going to be okay with that. We're not going to look at integrating over all the different layers to figure out its density. But yeah, this is the rotational inertia that we might use. How do I get omega? What is omega for the rotation of the Earth?
It's a random.
Yeah, so it's one period. Now, omega then would be equal to 2 pi over the period. One rotation would correspond to 2 pi radians. And then this is the amount of time that it takes. So 2 pi radians over a period. Okay, did we talk about the period of the Earth? What's the period of the Earth's rotation?
1 day.
It's actually not 24 hours, right? And why is that? It's very close. 24 hours is a very good approximation. But 24 hours is measured between what and what? Well, let's see. If the sun is directly overhead, or directly to the south, if the sun is directly to the south, and I set up an instrument and I anchor it into the ground, and I point it right at the sun, and then the Earth begins to rotate, and the sun moves away from that, when is the 24 hours over? When the sun's right at that angle again, yeah. So when the sun lines up with this again, that's 24 hours. Okay, during that time, has the Earth undergone one rotation?
Yeah.
Yeah.
And why not?
It's moving.
Because we're orbiting at the same time.
Yeah.
So here's what happens. Let's see. Here's an Earth rotation. No, I think I'm
There's one.
going to be here.
There's
So
one
I'm going to
over
be the
there.
Earth. Okay, the sun is right here. That's the sun. Here's a non-orbiting Earth. Okay, I'm lined right up with the sun, and then I start to rotate. You guys tell me when I've completed one rotation.
There.
Right there, right? And I'm facing the sun again. But as was pointed out, that's not the way the Earth behaves, because what's going to happen is the Earth is going to end up orbiting. So what I'm going to do this time is, I'm going to make this really hard. Okay, I'm going to start pointing in that direction. Right? You guys tell me when I've completed one rotation. Okay, see how I'm orbiting? And I'm rotating at the same time. This isn't really that easy. Okay. When have I completed one rotation? Right there. Am I facing the sun? No. It takes 4 more minutes until I face the sun again. So what that means is that the Earth's omega, or Earth's period of rotation for the Earth turns out to be very close to 23 hours and 56 minutes. It's almost exactly a 4-minute effect. So anyway, we can put that rotation, we can convert that into seconds, put in 2 pi over the period, come up with an omega, that would give us an angular momentum for the Earth. Now, this was angular momentum due to the, not the orbit, this was due to rotation. Is there also an angular momentum due to the orbit? Sure, there's got to be, right? If you've got something kind of going around in circles, that must also be angular momentum. How are we going to calculate that? How should we set that up to figure out how much angular momentum is in the orbit? So let's have the sun. I guess we'll put the sun right here. And I'm going to put the Earth in orbit like this. So here is Earth. Here is Sun. And what we're going to say is that the Earth is moving in some direction at some speed. Here is a distance. Here's a radius of the circular motion. If I imagine the Earth going around in circles around some center location, which is kind of where the sun is located, how much momentum does it have? And how much distance between the center of the circular motion out to the center of the Earth? You go, well, center to center is this Earth-Sun distance. That's like 150 million kilometers. And Earth itself is going to have a linear momentum of mv. Okay, how do we take a linear momentum like this and convert it into an angular momentum? Now we can do this. Let's see. Let's use the same idea as before. Let's try saying that L, now this is not rotational, this is what? This is orbital. So there's rotational, which we could think of as spin. So there's a rotational or a spin effect of angular momentum for the Earth. There's also an orbital effect. And the orbital effect would